Welcome back, everybody. This is Earth and Space Science 102. I'm your instructor, Stephanie Welch, and we have a really cool topic for you today. Today we're going to be talking about galaxies. So all along we've really been talking about stars from the perspective of thinking about them as single entities. And today we're going to really sort of look at how they're clustered together, how gravity holds together not just planets around stars and solar systems, but entire solar systems and galaxies. And we'll see that the universe has even a bigger and broader structure beyond that. And it's all gravity driven. So, to kind of put it into maybe a little bit of a scale that you might appreciate in your everyday life, if our solar system is akin to maybe the town that you live in, then a galaxy is like your entire country made up of thousands and thousands of towns. Now, we're not only going to talk about our galaxy, which is called the Milky Way galaxy, composed of at least 100 billion stars, each one of those stars with solar systems. We're going to talk about some of the categorization of some of the other galaxies out there in the universe. And as there are 100 billion stars in our galaxy, there are thought to be at least as many galaxies in just the observable universe. So let's just constrain this first of all to our own galaxy, which is kind of a little bit tricky. And there's a reason why it's tricky to kind of talk about our own galaxy, and that's because we're in it. So trying to understand the structure, the layout, the distribution of stars in our own galaxy is a little bit like trying to draw a picture of your house if you've never actually left your house. In fact, if you've never even left your bedroom in your house and you tried to, let's say, draw a picture of it from the outside, that would be a really incredibly difficult thing to do, to understand how it's structured and how many floors it has and so on. It's very similar with our own galaxy. And the reason why our galaxy appears as this sort of faint band of light on the horizon is because we are actually in it. So we see it head on. We see it from the perspective of being within the disk of the Milky Way galaxy. So because all of these stars are laid out in a disk, in addition to all of the layers of interstellar gas in the Milky Way galaxy, it's all distributed along this disk, then because we're in it, we see it as a line on the horizon. And it's really beautifully photographed in this picture with the kind of fish lens photography here, where you see it almost a little bit more rounded than it would be otherwise. If you were just looking at it through a normal picture, it would appear a little bit more like a straight line in the night sky. So what you're seeing when you're looking at the galaxy is not just the hundreds of billions of stars creating all of that light that light up that disk, but you're seeing it as that light has to travel through all of the gas. And so that makes it really difficult to discern, for instance, what's at the center of the Milky Way galaxy, the structure of some of these other stars, especially on the opposite side of the galaxy, and so on. And so again, all of this is made difficult by the fact that we're in it. Now, we can see above and below the disk of the Milky Way galaxy with relative ease, and we can see out into the universe, hundreds of millions of light years away. But looking through these layers of gas can be a little bit trickier. So even though we're seeing all of this gas in visible light as something that's going to obstruct our view of what's going on at, let's say, the center of the Milky Way galaxy and through the rest of the galaxy, when we look at this through other wavelengths of light, we can penetrate through that gas and we can see a little bit better the structure of the galaxy as a whole, and we can begin to kind of paint ourselves a little bit of a picture of what kind of a galaxy we're in. And this allows us to compare it to other observable galaxies out there in the universe. So this is a really neat picture that's showing you the Milky Way galaxy viewed from our perspective here on Earth, where we are on sort of almost out on the outer edge of the galactic disk, and you're seeing through all of those layers of gas. You can see it in radio waves, the longest wavelengths of light, to infrared, to the visible light spectrum, and then even in X-ray and gamma ray in the bottom two pictures. And every single one of these allows you to see something different different, something a little bit more unique and interesting. The shorter wavelength infrared picture, the fourth picture, shows you the distribution effectively of heat across the Milky Way galaxy. And you can see that there are more stars and higher temperatures closer into the center of the galaxy and lower temperatures towards the outside. And you effectively see the same thing in gamma rays, which is effectively seeing radiation in the bottom picture. So every single one of these pictures gives us something unique, a new twist to the story, and a little bit better of an idea of the structure of the stars in the Milky Way galaxy. So this is what we think the Milky Way galaxy would look like if you were viewing it from maybe outside, but still seeing it edge on. You would see the basic disk-like shape. So while the galaxy is 100,000 light years long, it's only 1,000 light years wide. And 1,000 light years wide is still, a pretty big chunk of space, meaning it takes light traveling at 300,000 kilometers per second, 1,000 years to travel from effectively the top to the bottom of the disk. But that still makes it 100 times longer across than it is wide, and so it still has effectively sort of a disk shape. So not only is it a disk in as far as the distribution of most of the stars and most of the interstellar gas that makes up the galaxy, you also have some other aspects to the structure here. You have these things called globular clusters that orbit around the center of mass of the Milky Way galaxy above and below this galactic disk. And each one of those is composed of perhaps 1 million stars packed together by their own gravity. And perhaps every single one of those stars has a solar system, just like our solar system. So those little bundles of stars orbit around too, but they orbit around a little bit closer to the center, a little bit closer to this area within the galaxy called the bulge. So the disk-like shape begins to lose its diskness. When you get a little bit closer to the center, you get a little bit more of a rounded spherical shape towards the center. And then finally, you have these halo stars, this halo effect essentially of having the light from the very center of the Milky Way galaxy illuminate a little bit further out, and these stars that again orbit above and below the galactic disk. So the entire thing is 100,000 light years wide. It means it would effectively have, if we're assuming that the Milky Way galaxy is effectively sort of in a perfectly circular shape, it would have something of a radius of something like 50,000 light years. So that means it's 50,000 light years from the very center of the Milky Way galaxy to the edge of the galactic disk. And then we're 28,000 light years from the center of the Milky Way galaxy out to where we are. So we're closer to the edge of the disk, closer to the outskirts, or the rural area in the galactic framework than we would be otherwise. We're about 3/4 of the way between the center of the Milky Way galaxy and the edge of the galactic disk. So that's the basic sort of overall structure, a disk-like shape with a bulge and with these halo stars. And you have also sort of an idea of where we are. Now, the interesting thing about all of these stars, the layout of these stars in the Milky Way galaxy, is that all of these objects are in continuous motion. They're in orbit around the center of mass of the Milky Way galaxy. And that center of mass is not just composed of one supermassive object in the very core, but the mass of all of these objects orbiting around relatively close to the center as well. It's really sort of, in a sense, the combined mass of everything within the galaxy packed together by gravity, and we're orbiting around that center of mass. So our solar system, our sun, Earth, so on all of these other 100 billion stars that make up the Milky Way galaxy, we're all orbiting around the center of mass of the galaxy in the same way that planets orbit around their stars. Now, if we could see the Milky Way galaxy from a different perspective, not sort of edge on from our perspective inside the galaxy, but let's say from above or below, then we think what we would see would be a characteristic spiral galaxy. And this is one of two main types of galaxies, as we'll see later. Galaxies called either elliptical galaxies or spiral galaxies. And the difference between them seems to be where the gas is concentrated, where the interstellar gas is not locked up in the form of a star, where that's located. And in the Milky Way galaxy and in other spiral galaxies, the gas is located within these arms that radiate out from the center, spiraling outwards. And then these types of galaxies are further denoted by how tightly wound those spirals are. So if we think that if we could see the galaxy, let's say from above or below, then we could see that we're on a star, we're orbiting around a star located within one of these spiral arms. The gas tends to be sort of isolated into these spiral arms, and that's where star formation is currently taking place. Now, with respect to star formation, it's worth noting at this point that the star formation is a constant process within galaxies, not just our own, but all of the other galaxies out there. The star formation and stellar death and that entire process of the evolution of a star is something that's constantly taking place. So it's something that I kind of wanted to kind of take a step back and remind you of from this much broader perspective than the perspective of a single star. This could be called galactic recycling, the process of creating stars and then allowing that gas to go back into the galaxy again to then fuel more stars. Or it could also be referred to as the star-gas-star cycle, however you like to refer to it. It's this process of forming stars and forming new stars from the wreckage of the old stars, a kind of stellar reincarnation. Now, if we wanted to pick a beginning and end to this cycle, we could start in this part of the cycle that I'm calling interstellar gas clouds fill the disk. And for that to happen, you first have to have the death of a higher mass star. That's where this gas is going to come from. That's going to be sort of the end of this cycle. So in the Milky Way galaxy, this gas not only fills out the disk, but it is concentrated in these spiral arms. And in these spiral arms, you can make mini stars. Now, in order for this to happen, we first have to, the way that we observe this happening within our own Milky Way galaxy is through many, many different wavelengths of light. And we can observe this process effectively happening every day. A new star forms in the Milky Way galaxy every day. And the reason why it forms is because this gas fills out the disk. Now, originally, this gas is extremely hot because it's formed from the wreckage of a dying star. So the second part of this cycle is that gas has to then cool and form new molecules again. And that's not something that forms in its original state when it's really hot, because all of those individual atoms are ionized. And that's why they're bright. That's why they're visible, why these planetary nebula and supernova remnants are actually visible from great distances, because that gas is hot and ionized. It cools over time. You form molecules. You form things like H2O, carbon dioxide, and so on. But the majority of these gas clouds are composed of hydrogen and helium. Then, once you cool off this gas, some, random motion, something going on outside that cloud of gas, maybe some distant supernova, causes this trigger to occur that allows the gas to start to collapse back in on itself and to spin. And the more it collapses in on itself, the faster it spins, and the higher temperatures get in the very core of this nebula. So we can see in the pillars of creation, this is one particular nebula within the Milky Way galaxy and countless other nebulas. We can watch new stars forming from the collapse of this gas. And one tiny little portion of the Milky Way galaxy contains enough gas to build thousands of stars and thousands of accompanying solar systems. So at the point when enough collapse occurs to generate high enough temperatures in the core to start fusion, then that system is stable for a really long period of time, especially when you're talking about this from the most common stars that are forming today, which are low mass stars. And then that fusion takes the form of taking that hydrogen and converting it into helium, maybe taking some helium, converting it into carbon, but not progressing on to the formation of the heavy elements that were a little bit more commonly formed back in the early days of the universe when high mass stars were a little bit more the norm, when temperatures on a whole were much higher. So we create these heavier elements, first stuff like helium and carbon, and in higher mass stars, you create even higher mass elements, eventually things like silicon and iron. And all of that is then returned back out into the galaxy once the star dies and throughout the star's life in the form of what we called in our solar system the solar wind, or the stellar wind in the case of other stars out there in the universe. These processes return all of those heavy elements out of the star and then sort of back out into the universe. But the ultimate way that this happens is once the star is no longer capable of maintaining fusion, either because it builds up iron in its core that it can't do anything with, or some other heavy element that it can't do anything with simply because it doesn't have high enough temperatures to succeed in more grand forms of fusion. And then those final elements form in the supernova event with a high mass star, or with the formation of a planetary nebula in a low mass star. So all of that leftover gas and all of these heavier elements are then returned out into space. You can actually see bubbles of gas forming around entire stars and entire solar systems as the stellar wind returns that gas out into space. So that's a really cool picture that you can see with all of this gas then returning back out into space. And you see very similarly awesome pictures of various planetary nebulas and supernova remnants as those heavier elements and even some of the lightweight elements, the gases like hydrogen and helium, are then returned back out into space. And then the final step that has to happen is that gas cools and blends into clouds, the kind of clouds that populate all of these spiral arms of the Milky Way galaxy. So this is maybe just another way of putting a process that we've talked about countless times throughout this class. When we talked about the conservation of energy and the conservation of angular momentum and the formation of our own solar system, we were effectively talking about the formation of a single star and the accompanying planets around that star. When we talked about this from the perspective of stellar evolution, we broadened our perspective to stars that are both lower in mass and in higher in mass than our sun, and we looked at how all stars form. This is just applying all of those same basic concepts, that stars form from the collapse of gas, and when they die, that gas expands outwards. We're just expanding that to looking at how stars form in our own Milky Way galaxy, and then we can apply that to other galaxies out there in the universe. So the other thing that I want to talk about specific to our own Milky Way galaxy is going back to the idea that all of these stars are in constant motion. They might move fairly slow compared to the speed in which a planet orbits around its star, but we do actually have some motion, both in terms of how our own star and our own solar system moves through the galaxy and how other stars move through the galaxy. So stars in the galactic disk, and that would include our own, because again, we're 3/4 of the way between the center of the Milky Way galaxy and the edge of the galactic disk. Stars in the disk move essentially in the same basic way that a planet would move around a star, with one main exception. Instead of taking a smooth path, like if you were looking at maybe a disk of sand on a record as the record was spinning around, instead of having this smooth motion where the object stays in the plane of the other objects, the stars in the Milky Way galaxy, including our own star, tend to move up and down as they orbit around the center of mass of the galaxy. So it's a little bit like being maybe on a merry-go-round ride, where you're sitting on top of that fake horse and that fake horse is moving up and down as it's moving around in a circle. The reason for this is thought to be the gravitational pull of all of these objects that are sort of slightly outside of the disk of the Milky Way galaxies, those globular clusters and those halo stars that are positioned above and below. Not only do we feel the effect of the gravity at the center of the Milky Way galaxy, we feel the effect of the gravity of these star clusters above and below that disk. And so they're kind of pulling us out of the disk a little bit. So we kind of bounce up and down as we're orbiting around that center of mass. So that's the disk stars. There are countless millions of stars located fairly close to the center of mass of the galaxy, and that's where things get a lot more complicated because you have a lot more halo stars above and below the galactic disk, just a lot more activity going on, and undoubtedly many collisions between entire stars and entire solar systems. So both the stars in what's called the bulge and the halo, which is a little bit broader in perspective, have much more random orientations than the stars in the disk. Instead of being mainly sort of bound to that same plane, mainly just kind of orbiting around that center of mass of the galaxy, roughly in a circle with that little bit of bobbing action going on, the stars in the bulge tend to orbit in completely random orientations. So not just around in that disk, but perpendicular to that disk and at oblique angles to that disk as well. So if you looked at everything as a whole, you could see the basic shape and structure of the Milky Way galaxy with the orbits of the bulge stars in red in this picture, fairly close to the center of mass of the galaxy. The orbits of the halo stars in blue with, again, their sort of random orientations. And then finally, the disk stars in yellow, being a little bit more bound to that disk. And it's just as much the kind of single moment position of all of the stars as also their motion that gives the Milky Way galaxy its overall structure. So it's not just the fact that if you captured it in a single frame in a single second, a star might have a particular position in the Milky Way galaxy. It's also a matter of how these stars move through the galaxy as well. That gives gravity the capability of structuring the galaxy in the way that we have it. Now, we're going to talk a little bit about the mass, both in terms of all of the stars close to the center of the Milky Way galaxy, the mass of the galactic bulge, and we're eventually going to be talking about the mass of the center of mass of the Milky Way galaxy itself, the sort of single entity that's, in a sense, holding the entire galaxy together. So anytime that we can detect two components of orbital motion, we can determine the mass of either object. We can use this to determine the mass of the moon by looking at the distance between the moon and Earth and the time it takes for the moon to orbit around the Earth. We can determine the mass of the moon or the Earth with that. That's Newton's version of Kepler's third law. And we can also apply this to the galactic bulge and even the center of mass of the Milky Way galaxy. In these terms, the two things that we need to know are the orbital period and the average distance, the perspective of the sun orbiting around the center of mass of the galaxy. And when I talk about the sun doing this orbit, our entire solar system, and of course Earth is along for the ride as well. So we're 28,000 light years from the center of mass of the Milky Way galaxy and from the center of this galactic bulge. So that is our average distance. That's the letter A in the p squared equals a cubed Kepler's third law thing that we were talking about a few lectures back. So that's one component of orbital motion that we need to determine the mass. The second is the time it takes to orbit all the way around the center of mass of the Milky Way galaxy. And that takes an incredibly long period of time. The last time we were in this same place in the Milky Way galaxy was before the dinosaurs evolved on Earth, 230 million years ago. That's how long it takes for our entire solar system and our star to orbit all the way around the center of mass of the galaxy, the orbital period. So knowing those two components allows us to determine the mass of first the galactic bulge and also the center of mass of the Milky Way galaxy itself. The galactic bulge, the sum of all of these stars and all of these other objects that are close to the center of the Milky Way galaxy, adds up to 10 to the 11th times the mass of the sun. And so that's approximately 100 million times the mass of the sun. Effectively something like the equivalent of 100 million suns packed together by gravity in this fairly small space. Now, all of that material is then orbiting around some center that's also extremely massive, and one might call this supermassive, to give you a little bit of a hint of what's at that center of the bulge. So the question of what lies at the center of the galaxy and what lies at the center of that galactic bulge, and not just the center of the Milky Way galaxy, but also probably the center of most galaxies, has been in question because the basic structure of the universe would suggest that you have to have fairly lightweight things with lower mass, and orbit around something with a higher mass. Our sun accounts for 99.9% of the mass of our solar system, and we on Earth and all the other planets are just stuck in orbit around the sun because we're bound to its gravity. In the same way, the sun and all of these other 100 billion stars in the Milky Way galaxy are bound to this gravity of this one very massive object at the center. And what we're going to do is zoom in on the center of mass of the Milky Way galaxy first into the center of the bulge, and then we're going to zoom in a little bit further from there. We'll first look at it from this perspective of a scale of 200 light years across, where in infrared you can see this bright red patch right in the very center. And if you zoom in on that and look at it in radio waves, it becomes even more apparent. You get these radio wave bursts fairly close when you're looking at it from the scale of 50 light years across. As we look at it even closer, again in radio waves, you can see that bright white object right there at the very, very center from this perspective where that bright white object is only maybe 1 light year across, the scale of the picture being 10 light years across. And if we zoom in even further in infrared, again seeing the heat, you can see stars orbiting around the center of mass of the galaxy. And probably the most fascinating thing yet is that we can't actually see that object in the middle. And when we see stars orbiting around it, particularly when there are collisions between entire stars and entire solar systems, those stars can then shift their orientation and end up careening towards the center of mass of the galaxy, where they disappear. They just vanish from our field of view. Entire stars, entire solar systems just appear to vanish. And so this last picture shows you that perspective from the shortest overall perspective, where we're not talking in light years anymore. We're talking in astronomical units. These closely spaced circles are showing the orientation of stars as they go careening in towards the very center of mass of the Milky Way galaxy to disappear forever. Not only that, there's an accretionary disk around this object where gas is at first really hot and highly visible, and then it disappears. So you may have guessed what object we're talking about at the very center, something incredibly massive, supermassive, but invisible. But I'll confirm it now for you. The object at the center of mass of the Milky Way galaxy is thought to be a supermassive black hole. Now, there are black holes out there that are closer in mass to the mass of maybe 3 or 4 suns. They're sort of somewhat low mass, normal black holes. There aren't a whole lot of black holes that have been found that have been somewhat in the middle category. And then we see many of these supermassive black holes at the center of galaxies. So we know that that supermassive black hole was once a star. And when that star died, a black hole formed that couldn't have been more than maybe 4 or 5 times the mass of our sun. Now, the black hole at the center of mass of the Milky Way galaxy contains the mass of 4 million suns. So what we can learn from this is that not only can a black hole form, but it can become larger over time as material is accreted and becomes part of the black hole. It's basically the equivalent of it's eating stars, it's eating mass, it's accreting gas into the singularity, and entire stars are being swallowed up in its wake. The larger it is in terms of mass, the more chaotic the motions of all of these objects that are in orbit around it, and the more collisions you have. The more collisions you have, the more changes in trajectory in these stars you have, and the more this material accretes, and the bigger it becomes. So our 4 million stellar mass black hole at the center of the Milky Way galaxy is thought to even not be that impressive on the scale of the broader universe. The biggest supermassive black hole that's ever been discovered is thought to have a mass of 20 billion times the mass of the sun. And I have a little graphic here that shows you what 20 billion suns looks like, packing them all up together in rows and in squares, and stacking those squares up on top of each other, and stacking squares of squares on top of each other. So this is all from the perspective of each one of those stars having the mass of our sun, and effectively the mass of most of our solar system. So this is what keeps a galaxy in check, essentially. This is what we think holds entire galaxies together and gives them their structure. These supermassive black holes at the center of those galaxies. So at this point, we're going to phase out of talking about specifically only the Milky Way galaxy and talk about the structures of some of the other galaxies out there that are both in some cases relatively close to us, and some that are much, much further away. Some that are in our own sort of cosmic backyard, and some that are on the other side of the observable universe. The first person to really start to analyze individual galaxies and to start to classify them based on their structure was Edwin Hubble in the 1920s. He demonstrated that galaxies could be divided on the basis of their shape and structure, mainly into one of two categories: elliptical galaxies and spiral galaxies like our own. There are other categories as well that are sort of side categories. One that's sort of a miscellaneous category we're going to call irregular galaxies, and one that's a subtype of spiral galaxies that we call barred spirals. Now, these basic two forms, the spiral galaxies and the elliptical galaxies, can be further subdivided on the basis of, in spiral galaxies, how tightly wound those spirals are, and in elliptical galaxies, just how elliptical their shape is. So in a spiral galaxy, you can range from SA all the way to SB, SC, and SD, with the higher letters, the closer to the SA, being more tightly wound spirals, and getting towards the SC and SD, more loosely wound spirals. So the gas in the interstellar clouds is still isolated to these spiral arms. But in the case of something like an SA, those spiral arms are wound a little bit more tightly. You have more spirals around the center of the mass of that galaxy than you do in maybe something like the SD, where those arms really do look more like arms, and they're just kind of spread out and distributed out from that center. The ellipticals range in shape from the E0, E being elliptical, to galaxies that are much more spherical, much rounder, to galaxies that are a little bit more stretched and more elliptical in shape, more oval in shape. When you get up into the E7 and so on, those are very elliptical galaxies that have a high degree of eccentricity. So those are the two basic types of galaxies, and I wanted to show you some examples of these. First, you have a series of pictures from different orientations of a classic spiral galaxy that's very tightly wound. Two or more arms spiraling outwards from that center. And the category of spiral galaxies would also include a category called barred spirals, where you have a rounded or elliptical mass at the very center of that galaxy, and then the arms distributed away from that mass. So it's almost like an intermediary category between the spiral galaxies and the elliptical galaxies. And the Milky Way galaxy, our own galaxy, is probably of this type, an SB or a barred spiral galaxy. The elliptical galaxies don't seem to have that gas concentrated in the arms. Instead, that gas is just uniformly distributed across the sphere or across the elliptical, depending on the degree of advancement of that elliptical shape. So they end up looking from greater distances, just like nice little sort of blob universes, very similar in shape to the globular clusters that are above and below the disk of the Milky Way galaxy. The irregular galaxies are neither elliptical in shape or spiral in shape. They maybe look like a thumbprint, or they may look like some kind of potato-shaped oblong, basically in any sense of the word, irregular galaxy. And Edwin Hubble believed that this was sort of the final stage of the evolution of a galaxy, that galaxies ranged from originally being sort of more spherical and elliptical in shape to being less spherical and more elliptical over time. And then they would range into either spirals or barred spirals as more time elapsed and as a greater degree of evolution of that galaxy elapsed. And then the final stage would be some kind of paint splatter appearance, irregular galaxy shape. So that's what Hubble believed, that every single one of these galaxies represented a step in this evolutionary process, where given enough time, a galaxy would range from an elliptical shape to a spiral shape and then eventually an irregular shape. That we weren't seeing really different types of galaxies, we were just seeing these individual galaxies in various stages of their evolutionary process. That's been largely discredited. That interpretation has been modeled as basically being incorrect. And we think that something unknown to Hubble is having a much basically has a lot more to do with its shape than it being in some stage of its evolution. Certainly, galaxies do change their shape over time as successive orbits of stars take place, because it's really the orbits of those objects that gives a galaxy its shape. But we think that its overall shape might have more to do with the presence of other types of matter within that galactic disk and the degree of the amount of other types of matter within those disks. Now, so far in this class, we've only talked about the sort of normal matter that's out there in the universe. We've talked about matter that's concentrated in stars and in planets and so on, and even stars that's concentrated in, matter that's concentrated in things like black holes and neutron stars. It turns out that this sort of quote-unquote normal type of matter only makes up about 5% of the universe. The rest of the universe is composed of this stuff called dark matter and dark energy. The amount of dark matter and dark energy is thought now to have a lot to do with the overall shape of a galaxy. The difference between the elliptical galaxies and the spiral galaxies having more to do with the amount of dark matter changing, having an effect on the shape of that orbit than really being a point in the evolutionary process of that system. So the idea of dark matter and what this dark matter is something that we'll talk about a little bit more in the very final lecture in this class. But for now, just no, it's a very strange form of matter, and that everything else that we've talked about in this class so far is not part of that category, that this is something that is completely invisible to us, and we can only see its effects. We can't observe it directly. The other possible cause of a galaxy type and the cause of a galaxy structure might be the result of collisions between galaxies. This is just a really cool topic I wanted to end today on. We can observe collisions between galaxies, and each one of those galaxies composed of 100 billion stars. Given enough time, entire galaxies can actually get into each other's way and collide into each other. And individual solar systems are thought to be mainly unaffected by this process, but you can observe in the case of distant galaxies colliding, and we will be able to see around around a billion years from now, we'll be able to see a collision between our Milky Way galaxy and our closest neighboring galaxy called the Andromeda Galaxy. There are 3 galaxies that make up a group of galaxies and a smattering of little tiny ones called the local group. And the 2 biggest galaxies are going to merge at some point. They're going to collide into each other. And the result of that collision, amongst other things, is going to be a complete change in the shape of both of those galaxies. They both start off as more spiral galaxies, and then as a result of those collisions, they become, both of them become a lot more elongated. And the initial collision will most likely result in a subsequent secondary collision, and eventually those galaxies will merge together. It'll probably take hundreds of millions of years for their original spiral shape to be regained, if it does, in fact, actually get regained. So that's just something interesting with galaxies that I wanted to close on, and it gives you a little bit of a brief glimpse into some of the material that we're going to cover in the very, very final lecture in this class. So in the very final lecture, we're going to talk a little bit more about the structure of the universe, how not only galaxies are oriented, but how multiple galaxies are all in orbit around each other, and how superclusters are oriented. And we'll talk about the beginning of the universe, this idea of how the universe has changed over time, and some theories on where we go from here and what the future of the universe looks like. So it's a really, really exciting final lecture. Until next time, keep looking up.